So perfect. Let's get started. Okay, so thanks a lot for the opportunity to speak here about MetricsReloaded. I think a few of you have heard about this effort. However, I want to go through a little bit of pitfalls, also recommendations, step by step, and tell you where we're currently at with this effort. But before going into details, I would like to emphasize a little bit on the successes of AI. So I think I don't have to tell you about it. I think all of us have been using all the great things that have been developed by ChatGPT, DALL-E. I think we will hear something about Segment Anything later. So given all of these successes, we sometimes tend to forget a little bit about failures. However, there are some quite dramatic failures actually of AI, and here I just listed a few of them. So things like AI really failing to recognize quite simple images, despising women, or just generally having some racial biases, having severe consequences in healthcare or systems that can be easily be tricked. So keeping in mind that AI can have very dramatic consequences when it's failing, how can we make sure that this doesn't happen? So I think one important part of this is proper validation. This always sounds a little bit boring. So you want to develop new models, you want to make sure that they're doing great things. However, if we're not validating them correctly, it could be very quickly end up in something really dramatic. And here you see also some more quotes of people telling you why validation is actually important. So things like, not even for AI only, but also if you can't measure something, you can improve it. So we need validation on the one hand to make progress, but on the other hand to make sure that our systems are doing what they're supposed to do. And also people from OpenAI are stating that it's actually one of the most overlooked skills in machine learning that we create proper evaluation schemes. So today I wanted to talk about one important part of the validation pipeline. So how do we choose proper metrics? Or in other words, why shouldn't we always use the common metrics that everyone else is using? So if you're developing in your algorithms, you will at some point need to decide how to validate it, which performance metric to use. Because typically you're not working with one or two images, you're working with hundreds and thousands of images, and you just kind of look at all of them qualitatively. So how do you choose the best metric? Because every one of them has been designed for a specific purpose, has pros, has cons, measures different properties. Do I choose one? Do I choose multiple? So how do I actually should do this? So we had a look at how people are doing this. For this, we had a look at competitions and their justification of why they took specific metrics. And here you see some of the answers that we actually saw quite frequently. So things like, yeah, this is a widely used metric. It's a standard computer vision metric. It's a common metric, indicating that many researchers are using metrics because of their popularity and not because they're really suitable for this kind of problem. This is, of course, not always the best choice, which I will show you in the next slides. But also, if you think of Kaggle, probably you know that, but for those of you who don't, that's a platform for hosting competitions. And if you want to do so, you have to pay for not using the common metric. So if you want to use your own metric that may be much more suitable than the standard things that you see on Kaggle, like AUC or accuracy, then you really have to pay for that. And that's, of course, a hurdle for many researchers. So we wanted to know which are the metrics that are the most commonly used ones. And here you see an overview of the metrics that are used among classification competitions. And we see directly at the top here, accuracy is the most commonly used metric. The problem with this is if you use accuracy, there are some problems. Class imbalance is something that very often happens in medical imaging. So probably you have seen this already with your problem. A disease, for example, typically just occurs not so frequently. So you have typically a class imbalance. And let's say we have a quite simple problem, like a binary classification into an email, spam versus no spam. So it's not nothing fancy. This is our data set that we have here, and we compute our algorithm with an accuracy of 97%. And you think, yeah, that's a great score. But if we closely look to our data set, we will find that it's heavily imbalanced. So we mostly only have the positive class in here, so the spam email, and only 3 cases with emails that are no spam. And if we then look closely what our algorithm is doing, we will see that an algorithm actually is always telling us that an email is spam, which makes it really useless in practice, but still we get this high score for the accuracy. The problem is that the accuracy metric is just not designed to handle class imbalances. And for this purpose, we should have used a different metric that is more suitable. For example, the balanced accuracy. And this is basically just the average of sensitivities per class. And this metric will then tell us that the algorithm is not as good as it seems with using the accuracy. However, this pitfall is very commonly known, and there are many memes about it. So probably you've already heard about that. So you could think of, yeah, well, balanced accuracy seems like a good trade-off, right? Because it handles this class imbalance issue. But balanced accuracy then has other drawbacks. So here I brought you a confusion matrix. You see we have not so many positive cases, actually many negative cases, and a very high number of false positives. So nearly 5,000 false positive predictions. And think of a scenario like screening. So we want to screen patients, and we have 5,000 patients that are false positive. So very critical in clinical practice. However, if we now compute our metrics, accuracy and balanced accuracy, both will be very high. So accuracy, again, nearly perfect, but still also balanced accuracy, although it's a bit lower, still has a very high value. So 85%, probably something that you would publish because it's a good value. Here, the problem is that the balanced accuracy, although it incorporates class imbalance, it doesn't look at predicted values. So it doesn't incorporate the false positives. And this is why the score is so high. If we have used something different, like the positive predicted value, we would have spotted this problem, or something else like Matthew's correlation coefficient, which is basically having a look at all 4 basic rates, positive, negative predicted value, sensitivity, and specificity. But then again, Matthew's correlation coefficient has other drawbacks that we need to keep in mind. So there's not the one perfect metric for any problem. And often it's not that we're just choosing the wrong metric, it's often also how we phrase our problem. So something that I often see in practice, that you have a detection task, but use a segmentation metric to validate this. And for object detection, we're interested in roughly localizing an object, not perfectly segmenting this, not having a perfect pixel-wise accuracy, only a rough localization, for example, with a bounding box. And you're doing a classification per object. So let's see what influence this has. So let's say we have this reference here. So we have an image from colonoscopy, where I work on quite a lot, and we want to detect polyps. In this example, we have 3 polyps, 1 large one, 2 tiny ones, and we want to make sure that we detect all of them to make sure that we're not just missing the tiny ones that can easily be cancer in the end. We have 2 candidate algorithms for this. Algorithm 1 only detects this large polyp and misses the tiny one, so this would be not a good choice, while algorithm 2 is actually detecting all of them. However, the bounding box of this large object is not perfectly aligned, but that's not a big deal. Because you were just interested in the rough localization. However, if we now use the segmentation metric here, we will see that this metric will tell us that algorithm 1 is actually better. Because this segmentation metric is interested in pixel level overlap. It's not interested in single objects. It's not interested in whether you have picked the tiny ones or not. It just looks at how much overlap do we have in terms of pixel. And in this term, algorithm 1 would be better. And this would, of course, a dramatic choice in a clinical scenario. One final example, sometimes we also want to have exact boundaries of something. So here we have a scene of bikers, and we want to do a binary segmentation like you see in this reference. And we want to make sure that our boundaries are actually good. So we have 4 potential algorithms, and I think we would all agree that not all of them are of the same quality. I don't know what happened to prediction 3, However, if we now use again our standard segmentation metric that we saw earlier, this metric will tell us that all 4 of them have the same quality. And this is, of course, not what we want here. So we would need to choose a different metric. I could talk about pitfalls forever. And if you're interested in this, please feel free to check out this paper where we collected many different pitfalls in a very comprehensive fashion. And also, if you know any more that are in scope, just let us know. We're always happy to include this. So we first wanted to uncover these problems, see what are the problems that we currently have in metric selection. And then we decided, okay, we need to do something about it. And we formed the MetricsReloaded consortium to solve this problem. And you see, we have many researchers from all over the world, an expert consortium. We have experts from machine learning, from validation, but also from statistics, prediction modeling. We have clinicians, biologists, all of them coming together with the aim to solve the metric issue. We wanted to come up with a problem-aware metric recommendation framework. We put 2.5 years of research into this with this very large international effort with more than 70 experts, and we used a Delphi process as a methodology. So we somehow needed to coordinate all of the different expertises. So we had a small group of coordinators. We were making some proposals like which metrics to use, which decision trees, what are the pitfalls that we need to take care of. We put this into a survey and gave this to the expert panel. With their different viewpoints, they then gave feedback. We analyzed that, put a little bit of update in our previously proposed things. We updated this, gave it back into a survey to the expert panel, and then we had this iterative nature so that we could really come up with an expert consensus on the recommendations. And the important part here is the problem-aware metric recommendation framework. So we are not suggesting to always use the common metrics, so we have them in the framework, but we are really suggesting to come from the driving research problem and end up with a very specialized metric recommendation for this problem. We do this by using what we call a problem fingerprint. So we really, in a structured way, capture all the relevant properties that we need for metric selection. And I will explain this in a second in a little bit more detail. Here, it's really common for your research problem, like the fingerprint of your hand. And given with this fingerprint, we then have a look at which is actually the problem category. So is it classification or semantic segmentation or whatever? For each of the different tasks, we have metric candidates, and based on the fingerprint, we decide what are the best candidates for this very specific problem. And as I said, in the problem fingerprint, we're capturing all of the different properties that we need for metric selection. So based on the pitfalls that we found, we formulated these points. So here you see a selection of them. For example, are we particularly interested in structure boundaries? So think of the example that we saw earlier with the bikers, where we want to have like good boundaries, good contours of the object. Here we would have needed a different metric. However, if we're only interested, for example, in the center of a structure, we don't need a metric that really cares about contours. Then we have different things like, do we have small structures? Do we have high variability of sizes of the objects? Do we have class imbalances? Are the test cases independent or not? All of these things matter, and we incorporate all of them in form of decision trees in our framework. Before I go into detail with how the framework looks like, I want to emphasize that given this problem fingerprint, we can now really generalize across domains. So it's not important whether you have a medical image or just something like a standard photograph or satellite. It's only important that we have an image and that we do a classification task. And here we define the classification at 4 different levels. So we start with the standard classification case actually, so image level classification. We could also do the classification at object level. So what we saw before. So we draw a bounding box, for example, and we classify this object then. We could do a pixel level classification. So for each pixel, we say which class is it foreground or background, and all of those things, which would be a semantic segmentation. And we could also combine object and pixel level classification to an instance segmentation. So having these in mind, let's look at the framework. And it looks quite complex at the first glance, but we will go through it step by step. We start with a problem fingerprinting. So as I mentioned earlier, we answer all the different questions. So what is important to us? How do my images look like? What objects do I have? And all of those things. Based on this, we will then make sure that we generate the correct problem categories so that we're just making sure, do you really have object detection, or perhaps is it more a semantic segmentation, those things. After we did this, we used the problem fingerprint for the metric selection. And this is the largest part and basically the main contribution of this framework. And here you see we have arrows in 4 different colors. And the colors indicate which problem category you have. So image level classification, object detection, instance segmentation, or semantic segmentation. And if we now just follow the blue path, for example, we will first come to this node here, which states select multi-class counting metric, if any, and then we have this plus symbol S2. This means, so we now want to select a multi-class counting metric, so a specific type of metric. And this plus symbol means there's a decision tree behind this. So I will show an example of this in a few slides. But generally, this means based on the fingerprint and these candidate metrics here, you will be guided through this decision tree and end up in the best fitting metric candidate. Or you end up with nothing, depending on your problem. But we wanted to make sure that you're using different metrics. So we're recommending to not use only one metric, but to use multiple ones to comprehensively assess what your algorithm is doing. So after selecting a multi-class counting metric, you select a per-class counting metric, a multi-threshold metric, calibration metric, before you then go to the following steps. And depending on which problem you have, you would just follow the colored arrows here. And in the final step, we then give some recommendations on the metric application. So things like how to determine a global decision threshold, how to aggregate metrics, how to report them, and all of those things. But I think it's always much easier to look at this with a concrete example. So let's now focus only on semantic segmentation, so only the yellow path. And let's be more specific. Let's say we want to segment large objects. So we have 2 potential scenarios here as examples. For one thing would be lung cancer cell segmentation from microscopy or liver segmentation from CT. Again, let's have a look at how the pipeline looks like if we only look at semantic segmentation, and it directly looks much easier, right? So we don't have so many things to keep in mind. So we start with generating the problem fingerprint, and then we select an overlap-based metric. So a metric measuring the pixel overlap between the reference and the prediction. We have 4 candidates, and let's have a look at how this decision tree actually looks like. So this is the decision tree, and I already marked the path that we go using our answers from the fingerprint in bold here. So we start, we have been told that we should repeat this for every class. So given that we only have a foreground and background, we typically only look at foreground. This is also what this info box and at the top states. Then we check some exclusion criterion if we really need such a metric. In our case, we do. And then we follow the path, and we are getting to the first node, which is basically a combined question of the fingerprint. Are we exclusively interested in the center line of structures? In our case, we're not, but this could be important for other applications. Think of something where you have a very thin or a tubular shaped structure, something like airway trees or vessels. Then this would be important. So in our case, we say no. We go to the next node, the next fingerprint question, which states unequal severity of class confusion or over segmentation versus under segmentation. Are they equally severe? In our case, yes. It's not important whether we're segmenting too much or too less, but in some applications, again, this may be important, like radiotherapy, where we would like to make sure that we're definitely treating all the sick tissue. There we would have an unequal severity. However, in our case, it's both equally severe. And we here in this end node select from DICE or IIU, and it mentions a decision guide. So what is that? So while we're constructing these decision trees, we came to the conclusion that we just couldn't consider every potential use case that exists out there. And sometimes it's really more a kind of a preference. So this decision guide will actually help you to take the final decision. It discusses pros and cons of the metrics, the different pitfalls, and perhaps for your specific research question, one pitfall is just not important. So you could just use this metric. In our case here, this decision guide would basically tell us that the metrics are more or less the same, and more a question of which preference, so which community you're in. So given that we're in the medical community, we're here using the DICE. Then we continue back to the primary path, and then we select a boundary-based metric. So a metric that really has a look at the contour accuracy of our algorithms. Here you have a different decision tree, and again, I marked our path in bold here. Similarly to before, we check if we need such a metric. So here we have different inclusion criteria. For example, if we're interested in the boundaries, then we should definitely use a boundary metric. So we need such a metric. And then the first question here is, do we want to compensate for annotation imprecisions? So especially in medical imaging, you probably have already seen that experts often disagree in the annotation. And since this also appears for our problems, we would like to have a metric that can compensate for this issue, because we don't want our algorithm to be penalized for something where the experts don't agree, right? So we can use the normalized surface distance over here. So the NSD, which actually comes with a threshold where we can say which tolerance do we actually accept. So after we selected the DICE and the NSD, we go back to the primary path and to the node select application-specific metrics. And this node we included because we wanted to make sure that you could really, as it says, select a very application-specific metric. So sometimes you just have a metric that is very specific for your research problem, or you have something that is newly developed, something like this. And we just wanted to give people the opportunity to really also use their metrics that are really specific. In our case here, for liver segmentation, if you talk to clinicians, they're typically not interested in our technical measures. They don't want to have a look at the NSD value. They just want to know what is the volume of the predicted liver. And this is why we added the volume difference here as a metric. After this, we could also, if we want, select some metrics that are not reference-based. So things like the carbon footprint of your algorithm, the runtime, the memory consumption, to assess also these properties. And then we're already at the metric application, where we aggregate the results into a ranking, for example. I hope with this example, I could make it a little bit more clear how this actually works. But still, the framework is quite complex. And if you look at the paper, you will probably get a heart attack because it's, I don't know, more than 100 pages, definitely long. And so we wanted to make this very accessible to the community. One of the first measures that we took is we instantiated the framework for common biomedical use cases. So we asked the community on Twitter, what are the use cases for which you would like to see a recommendation? And we compiled a list of them. We built expert groups. We made sure that we got a fingerprint for this. And here you see the recommendations for the different use cases. So we also have more. And we hope that already some researchers find their exact research problems over here. But while we were doing our research, we found that it's really difficult to just collect all the information for one specific metric. And it's really annoying if you want to find something specific or you just don't know about it. You want to inform yourselves what are the problems or whatever, and you just don't find it because it's scattered across different resources. And typically a publication assumes that you already know everything about a metric. So we compiled cheat sheets for every metrics in the framework. So you see 3 examples here. So a sheet for every metric with all the relevant information for these problems. So for example, like standard things like the formula, but also the value range, which is not always obvious. Or if we can extend this metric to multi-class. relations to other metrics, or things like prevalence, dependency, what are pitfalls, what are recommendations. So all of these information in place, and it's definitely something worth to look at. I still use it in practice because you also tend to forget things, and this is really helpful. Also, we wanted to highlight how metrics relate to each other. So we have this table over here. The concrete formula dependencies are in the cheat sheets, but here you see at one glance what are actually synonym metrics, which also happens. And I also saw this in publications that they actually used identical metrics, although yeah, they just have different names, which are slightly dependent, which are dependent on each other. And this, I think, is also quite helpful. And what I think is interesting for most of you today, as Stephen already mentioned, we implemented these metrics in MONAI because we also found that the implementations often differ also across standard libraries. And then you have different results when you're using sklearn with the torch metrics, for example. And this, of course, shouldn't happen. And here we implemented the way that we found most suitable based on our research. And here, thanks to Carol, who took the lead of this initiative. So you find this under this link here. So we're not finished yet. We want to improve some things. And this is also where we would like to have your help, if you wish. So we are currently compiling a list of things that we would like to test. And if you would like to contribute here, we would be happy if you would just put your name and email address in this table here. I would put the link later in the Discord. We would then contact you with some further explanations of what to do. And we are also happy to highlight your contribution in the GitHub. And also we're planning to write a paper on this implementation, but here we just need some time. So if you're interested, we would be very happy for your help. Yeah, and one final thing to mention, we're currently working on making this whole framework into a toolkit. So we're implementing this online tool. So this is a demo version where you see you just don't need to read all the background work. You're just generating everything on the fly. You're generating the fingerprint on the fly. You're just answering some questions. You're giving some explanations of what we mean with the specific questions. You just say yes and no based on your research problem. So basically all the decision trees are in here, just working, running in the background. And based on your answers, you would then be given the exact same answers and metric recommendations if you have just used the recommendation framework. So if you would like to use this, this is still the beta version. So you will see that it is password protected currently, but just write us an email. We're happy to share the credentials. We just cannot share it openly right now because the paper is still under review. But just let us know. We're happy to share. And also, if you have some feedback, let us know. It currently doesn't look as nice as this. It's just, yeah, a beta version online. Yeah, with this, I would like to thank you for your attention. I'm now happy to take any questions.